Welcome back. In this brief lecture, we will introduce some components of a bipolar fuel cell. This is fairly a descriptive lecture, not very conceptual, but you need to know these jargons that come with a um, bipolar fuel cell. So the basic components are schematically illustrated here. So we can probably start from here and start the description. An electrolyte is an ionic conductor. So the electrolyte should have minimal conductivity for electrons and also for anode gases and cathode gases. In a way, electrolyte serves an important purpose of separating the anode gas from the cathode gas, because if they mix together, there can be thermal combustion, uh, which you don't want to happen. It's a big safety hazard. So the electrolyte plays this important role of separating anode gases from the cathode gases. So the flow fields indicated here, here and here and here, um, allow for the distribution of anode gases and cathode gases. There's a bipolar plate, or this is given the name interconnect for in the case of solid oxide fuel cell. Both are one and the same. In a way, on one side, anode reaction occur. On the other side of the bipolar plate, on this side, you may have, let's say on one side, there can be cathode reaction. On the other side, you may have anode reaction. So in the next slide, we would talk about a few additional aspects. There is this aspect which is not indicated here explicitly. This aspect is called the gas diffusion layer. It is a porous layer. One of the main purpose of the gas diffusion layer is that when you have a bipolar plate like this, the area underneath these regions should also be active, right? So if the gases come in like through these holes, the gases should be able to reach these places so that the entire electrode surface area is available for the electrochemical reaction. So the gas diffusion layer is often very thin, maybe about 200 micron thick. It is porous. It is also an electronic conductor, and it allows for uh, the passage of these gases too. So you should relate the gas diffusion layer to concepts which we have covered in the past, especially on the three-phase boundary in a porous electrode. Please look at the previous lecture on this topic. Moving on. Okay, one more thing is an important aspect of a bipolar plate is that it should be a good conductor of electrons, right? That's the main thing. The role of a bipolar plate is to conduct electrons from one anode to the cathode, current from one side of the electrode to the other side of the electrode. So it should be a good electronic conductor. And because it's exposed to two different kinds of gases, anode gases and cathode gases, there are certain material constraints that are critical for a bipolar plate. But this course is not about materials. We will not elaborate further on this, except to state that a bipolar plate should be a good electronic conductor. To get an idea of the volume of a fuel cell stack, this picture is useful. There are some jargons which are not too important. what is important to understand is this area is a measure of the electrode surface area. So manifold means a way to distribute gases. So there are there is the fuel are let into the fuel cell stack from this side, and the unused fuel gets out in this side. Perpendicular to this direction, air, which is the typical oxidant, gets in this direction and gets out in this through this side. So this is indicative of the active electrode area. What we are looking here is in a direction perpendicular to this. Okay, for example, if you're viewing from in this direction, you would see this. So there are different cells. That's what we mean by repeating elements. There are different cells stacked together to form a stack. So the stack length divided by the thickness of each of the element will give you the number of cells. So the entire volume of the fuel cell stack can be computed by stack length to cell width times the area available here. That would give you a measure of the volume of the fuel cell. So again, here the fuel is let inside into the stack in this direction, and the fuel gets out in this direction. So in the next lecture, we take up an important topic of what should be the utilization of the fuel and oxidant. What is the trade-off if you utilize too much of the fuel and oxidant, or if you use too little of the oxidant and fuel cell? That would be taken up in the next lecture. Thank you.